Hello, and welcome to your second Markov chain Monte Carlo lecture. All right, so we spent the last lecture talking a little bit about the challenges that come with sampling from some probability distributions and ways that we can sample from them. The main algorithm that we talked about was the Metropolis-Hastings algorithm, which is a really simple form of MCMC. Now remember, for Metropolis-Hastings, what we are basically trying to do is have this iterative process where we can randomly propose a candidate state from our distribution using some proposal distribution. And then we want to have a rule about whether or not we're going to accept the proposal or reject it. Remember, we're choosing these things in a way so that the final samples we get are from the distribution that we want to target. Here's some R code that sort of implements the Metropolis-Hastings algorithm. So to do one step, a Metropolis step, essentially we have to generate a proposal, decide whether we're going to accept it, and then, accept it or move on. So in order to propose something, one of the things that we can do is we can essentially use a random normal distribution that is centered around our current value and use that to randomly generate our proposed value. That's what this line is doing right here. Once we have this proposed value, we need to decide if we are going to accept it or not. Now remember, we want to accept, for the most part, values that are likely under our target distribution. So the rule for acceptance is going to be this: the minimum of 1 versus the target of the proposed value divided by the target of the actual value. Essentially what this is comparing is the likelihood of our current value versus the likelihood of our proposed value. Notice, in this little fraction, when the proposed value is more likely than the value we currently have, we are always going to accept this new, more likely proposed value. However, when our proposed value is less likely than our current value, we'll still sometimes accept it, right? Sometimes rare things happen, but not a lot. And so we're going to accept in proportion to how likely it is. So this acceptance probability basically determines how often it is we are going to accept the new value. Always if it's more likely than the current value, sometimes if it's less likely. Then we just run a little Monte Carlo simulation to determine if we're going to accept it, and we're done. We've either accepted our value and returned that, or we've rejected our proposed value and we continue using the current value. Now, of course, that's only one step. We also need to be able to repeat this over and over to actually get a bunch of samples from our distribution. And that's what this code does. It just runs that Metropolis step iteratively over and over and stores all of our samples, right? Either that's going to be the new proposed value or we're going to keep the current value again. So for instance, if we wanted to sample from this distribution, which has this formula here that I'm not going to read out loud, we can essentially just plug that in as our target value and then run the Metropolis-Hastings algorithm over and over and over again. So this is the distribution that we're trying to sample from. And maybe just by looking at it, you can see why it might be a little complicated to sample from. Essentially, we want to sample from this distribution without having to analytically calculate what this function actually is, because for some reason that may be either very computationally difficult or just something we don't have access to. Now, when we run this algorithm over and over, you can see that the samples we get are going to start looking a lot like our target distribution, right? We chose our proposal and our acceptance rule in a way that allows us to have some various guarantees that in the long run, our samples will converge to the target distribution. But there's a couple of different things from the Metropolis-Hastings algorithm that we didn't cover that can help the algorithm be more or less efficient. The three things we're going to talk about today are the proposal width, the burn-in period, and thinning our chains. The proposal width is basically just a hyperparameter in our Metropolis-Hastings algorithm that tells us how far from the current value we'll allow a proposal to be. For instance, here you can see some samples from the Metropolis-Hastings algorithm where the standard deviation of the normal distribution we're using to propose new values is 1. You can see that it kind of can jump all around because the standard deviation of the normal distribution we're using to propose samples is pretty wide. We might get new samples that are pretty far away from the current sample we have. Here's an example. When we lower that sigma, we reduce the variance or the proposal width. This is looking at a proposal width or a standard deviation of 0.25. In this case, you can see that even though we're still doing something similar as we're exploring this space, we do so much more slowly because the steps that we can take away from our current proposal value, or from our current value with our proposal value, is much smaller. So you can kind of see these little steps that we take. We're not able to kind of go up and down really fast. We can make little small adjustments at every single step. Now remember, no matter what we change our proposal width to, we still have to reckon with our acceptance step, whether or not we're going to accept the current proposal or not. Now, it does say the answer on the slide, but I want you to look at this trace plot for a second. Why do you think the trace plot looks like this? Here we have a normal distribution for proposing values that has a standard deviation of 100. That means when we're looking at our current value and we're trying to generate a new value, the standard deviation of the distribution we're using to propose that value is 100, which means we can propose new values that are very different than the current ones that we have. Now, I want you to take a second, pause the video if you need to, and think about, okay, what about that would make my trace plot, looking at all of the different samples over time, look like this? All right, hopefully you've paused and thought about it, but think about this a little bit more. Why would it look like that? Well, if we have a proposal distribution with a standard deviation of 100, we can propose really big and really small numbers compared to the value that we're currently at. But are those values likely under our target distribution? Probably not. And so what you're seeing here is essentially we're proposing pretty extreme values, and so they don't often get accepted. And what happens in the Metropolis-Hastings algorithm when we don't accept a new proposal, we stick with the current value, which is why you see all of these plateaus here. What's probably happening here is extreme values are getting proposed, and it takes a while for us to get one that actually is relatively likely and has a high chance of being accepted. So the proposal width essentially allows us to propose values that are more or less similar to the current value we have. And again, like most things in statistics, there's basically a Goldilocks zone. We don't want to propose things that are so different from what we currently have because ostensibly the value we currently have is probably a relatively likely value under our target distribution. So we want to be able to propose something that's at least relatively similar to what we currently have. However, we also don't want to choose a proposal width that's too small because as you can see, it leads to these super correlated samples. We can move around the target distribution and get different values from different places in the distribution, but only slowly. We basically have to take these little baby steps every single iteration. We can't move that far from where we came. So like most things, we essentially want to choose something in the middle, something that's not too big, causing weird issues like this, and something that's not too small, which basically means we have to take these little baby steps as we are traversing our target distribution. All right, the next thing we're going to talk about with the Metropolis-Hastings algorithm is a burn-in period. A burn-in period is basically a chance for the algorithm to escape from its initial conditions and converge to the target distribution. Remember, one of the things we talked about in the previous lecture is that we are basically choosing the algorithm, like the way the algorithm works, so that the target distribution, or excuse me, the samples that we get are eventually going to be from the target distribution, but it doesn't guarantee that they'll immediately be from the target distribution. For example, what if we initialize our algorithm at a value that's pretty unlikely for our target distribution? Well, depending on things like the proposal width, it might take a little while for our algorithm to kind of get to the point where it's sampling from our target distribution. You can sort of see this in these plots here. We initialized our value to something that's pretty extreme under our target distribution. And so you can see it's taking these little steps here and there to kind of get around the values that we expect. You can see here that the kind of average value for this distribution is maybe a little bit higher than 0, but around 0. And so it essentially takes a little while for the algorithm to walk up there and then start sampling from these values. And of course, this looks way more complicated when we're sampling from more complicated distributions, but I think that this gives you a pretty good idea of why we might not trust the initial samples that we get. Maybe we haven't converged to our target distribution yet. So maybe we're not actually sampling from that target distribution, and therefore we maybe don't want to consider those samples. Here you can even see when we plot out the target distribution in red versus our samples in this histogram, you can see that lower values are far overrepresented because our chain started and had to sort of gradually ease its way out before it probably ended up converging and sampling from our target distribution. So what do we do with that? I mean, one way you could maybe think about it is if we ran our algorithm for like thousands and thousands and thousands of samples, eventually the behavior of the very beginning wouldn't matter that much. However, one, that's really computationally expensive, and two, we don't necessarily know how long it's going to take to start converging to our population distribution. And so one of the things we can do is have a burn-in period. Burn-in is really conceptually simple. We essentially let our chain run for a bunch of iterations before we actually start collecting and recording the samples. Essentially, we're giving it time to get to that converged state, and then we start recording the samples. Here you can see that same chain as before, but we have a burn-in period of about 200 iterations. This means we're giving the model about 200 iterations to kind of find its way to the target distribution, and then we start recording. And as you can see, the samples that we get from this with the burn-in period accounted for are a lot more similar to the target distribution. We don't have that super overrepresentation of low values like we did without the burn-in period. Okay. So the last hyperparameter for Metropolis Hastings that I want to talk about is thinning. Thinning, in essence, is taking all of the samples from your chain and essentially removing every n samples, or only taking every n samples. So for instance, if we have the trace plot at the top, you can see that there's a lot of autocorrelation, meaning that different samples essentially affect the samples around them. You can see that happening here. In fact, this is something we sort of talked about earlier when we talked about the proposal width. When we have a proposal width that's too small, your next sample, even if it's moving a little bit, is going to be very similar to your current sample. And that's going to keep happening. And we're going to get these correlated chains of values. Now you might think, okay, who cares? The sample's similar to its neighbor. What does that even matter? Well, the reason that it matters is we're trying to use these samples to approximate a target distribution. And we have really correlated samples. We're essentially not getting a lot of new information with every sample. And so one of the things we can do to combat that, if we see really heavy correlation, autocorrelation in our chains, meaning, values are really correlated to the values around them, one of the things that we can do to get around that is just thinning the samples. If your current sample is really correlated to the previous few samples, why don't you just take every 10 samples instead so they're less related to each other? That's exactly what thinning does. And essentially what we're doing here is we're trying to overcome that autocorrelation, and we're willing to sacrifice the computational complexity of getting more samples with getting samples that are uncorrelated, or at least less correlated. So at the top, we have a chain that you can see that there's pretty heavy autocorrelation in the samples. One sample is very similar to its neighbor samples. And then the bottom, you see a different chain where we've sampled a ton more samples. We've sampled, what is this, 50,000 samples instead of 1,000. And then maybe we take only 1 out of every 50 samples, so that instead of seeing this heavy autocorrelation, we see this relatively uncorrelated chain of samples. Remember, when we have really correlated samples, they're still giving us information about our target distribution. However, the more autocorrelated they are, the less information each individual sample is actually giving you. All right, so we talked about Metropolis Hastings and the basics of how it works in the last lecture. And today we talked about some tweaks or some hyperparameters that we have to work with when using the Metropolis Hastings algorithms. First, we have proposal width, which basically determines how far away from your current value you're able to go when proposing a new value. We don't want this to be too high because it will propose things that are completely unreasonable, but we also don't want this to be too low because it'll be too slow to actually change that value, because every single value is going to be a little itty bitty baby step away from our current value. Next, we talked about burn-in. Burn-in essentially are extra iterations that we don't record, and it gives the MCMC algorithm time to converge to the target distribution. Remember, when we use MCMC, we are choosing the way that the algorithm works. We're choosing things like the proposal distribution and the acceptance criteria. We're choosing those in a way that eventually it should converge to our target distribution. But notice we said eventually. We don't know that it is converged immediately. So the burn-in period is essentially an amount of iterations that allows us to give the algorithm time to hopefully converge to our target distribution. Now, we still need to check if it has converged, because maybe we gave it 1,000 and it needed 5,000 iterations to converge, but at least this gives us a little bit of wiggle room to basically give it some time to reach the target distribution, and then we start recording our samples. This allows us to get actually good samples that are not biased towards whatever the starting value was. Lastly, we talked about thinning. Thinning is essentially just generating a ton more samples than we want in the end. And instead of looking at every individual sample, we look at every n sample. So maybe we generate thousands of samples and take every 10. The reason we might do this is because if we see high autocorrelation in our chains, meaning every single value is really similar to the next value that we've accepted in that chain, then we're not getting a lot of independent information about our target distribution. And so we may want to thin those samples so that each individual sample is not as autocorrelated with the ones around it. Again, what we do is if we need 1,000 samples, we might generate 10,000 samples and then only take every 10 iterations instead of every single iteration. All right, that's all I have for you. I will see you next time.